Good morning, students. So today we'll study estimation, chapter number 7 of the book by Leaf, and we'll now in this chapter basically we'll try to estimate population mean from sample mean. Under estimation, we'll try to understand these two terms, point estimate and interval estimate. Now, if you have taken a sample out of population and calculate its mean and standard deviation, and we have to estimate the mean of the population. Now, if we say we have taken 30 samples and we have taken all their means, 30 means are there, and we'll take the mean of means. Obviously, that will give you a point estimate of the population. That will give you an idea about the mean of the population. But for more accuracy, we need to go towards interval estimation, where we will say like this: from this number to this number, mean will lie at 95% confidence level or at 99% confidence level. Basically, what I am saying is we have to find the interval. Interval means we'll give a range of numbers, that from 8 to 10, from given two numbers, between given two numbers, the mean of the population will lie. Now we'll try to understand how we will calculate this interval for different categories. For understanding the calculation of interval estimation, we need to understand central limit theorem. Don't get confused. It is very simple single line statement, which the result of which we use in the calculation of the interval estimation. What central limit theorem says that if there is a population which is not normally distributed, even if that population is not normally distributed, and we take repeated sampling, if n is greater than equal to 30, around 30 samples we are taking from that population, suppose, and we take the mean of those 30 samples, so we'll get 30 means. Now, if we prepare a sampling distribution of means of sample size n, that will always be a normal distribution. This is central limit theorem. I am repeating again. Central limit theorem says that the sampling distribution of sample means approaches a normal distribution as the sample size gets larger, no matter what the shape of the population distribution. So basically, the thing is, even if the given population, the given data is not normally distributed, the sampling distribution of means will be normally distributed, and it will be more normal as the sample size gets larger. And large sample means n greater than equal to 30 we call large sample, and n less than 30 we call small sample. N greater than equal to 30 we go for Z distribution or normal distribution tables, and for n less than 30 we go for T distribution tables. Okay, now what do you mean by standard error? We'll just define this term. Now, I have already said that if I take 30 samples from a population and take the mean and standard deviation of this, so I'll get one mean of means and one standard deviation of means. Now, this standard deviation of means and a given sample can be correlated by sigma x is equal to sigma upon root n, where sigma upon root n, the new standard deviation, which is the standard deviation of sampling distribution of means, is called standard error. So So now we'll try to understand different formulas for calculation. So first we'll understand confidence limits for mean, population mean. If it is a large sample, then we'll go for Z distribution, and if it is a small sample, then we'll go for T distribution tables. So now here X bar is the sample mean, sigma is the sample standard deviation, N is the number of samples, and Z is a reading, which is, if you can learn, it is 1.96 for 95% confidence level, 2.58 for 99% confidence level. Otherwise, you can see the table. And if the sample size is less than 30, we'll go for T distribution table. So we'll just X bar plus minus Tk alpha S upon root n. So we'll just replace the Z value by T value. Now the second category of questions is confidence limits for the difference between two means. Suppose we are given two means and we have to estimate the difference between two means. As we'll do the questions, you will be able to understand it. Just go through the formulas first. So here we'll just take the two sample means and take their difference. And now this is the standard deviation of two samples, and these are the N1 and N2 are the number of samples. Some sample size of the two samples. And in case of small sample, we'll be using this formula for calculating the for the difference between two means, as for estimating the difference between two means. And now here a new term comes, that is matched sample or paired sample. This is something we need to understand, which is very important, and we'll be using this term afterwards also. Now if you are given two datas, and suppose I take the marks of batch A and I take the marks of batch B. These are independent sets of data. There is no correlation between marks. Any number can be there in batch A and any number can be there in batch B. So this comes under independent data, independent samples. Now we'll try to understand the meaning of matched sample or paired sample. So matched sample or paired sample means, suppose A batch, these are the marks of A batch in first year, and we are comparing the marks of the same A batch in third year. That means roll number 1 marks in first year and roll number 1 marks in third year we are trying to compare. So there is some sort of connection in the readings in the data given. So that is called matched sample or paired sample. So you need to identify the question ki matched sample is given or independent sample is given. Accordingly, you will apply the different formulas. So for example, we can say if there is a fabric and the fabric is same and we are giving two finishing treatments to compare the finishing treatments, not fabric. So same fabric, when we divide it into two parts and two finishing treatment A and B is given, and we need to compare the data of A and B, that means we need to go for matched sample or paired sample. So we'll just do one example related to this. This is your chapter 7 problems given in exercise. So we'll do first one here and then we'll continue in the next class. So in the first example, we'll try to understand. A sample of 150 specimens was tested for carbon content. The mean of the test sample was 4.4% and their standard deviation was 0.18%, and we have to calculate 95% and 99% confidence limits for the mean carbon content of the population. So what data is given here? We are given that it is a large sample question because n is equal to 150. Next, mean is given, that is 4.4, and standard deviation is given as 0.18. So we have to calculate both 95% and 99% confidence limits. For 95% confidence limits, we'll go for 1.96 at Z value, and for 99% we'll go for 2.58 Z value. Now we can see here sample mean plus minus 1.96 into standard deviation upon root n. So we'll just put in the values and calculate this range. So what we are doing here, we are given the sample mean and sample standard deviation, and we are trying to estimate the confidence limits of the population mean. That means we are sure that we are 95% sure that population mean will lie between 4.4 plus minus 0.0288. Where this is the error. This is the error term. So this is one example of interval estimation. Similarly, you can find out the 99% confidence limits for population mean. If you will put the value 2.58 here, and we are 99% sure that our population mean will lie between these two values. Thank you. We'll continue in the next class.